you, Vanya. Thank you very much. And so it is really a great pleasure for me to introduce our seminar speaker today, Professor Naveen Verma. Um, Naveen got his PhD from MIT in 2009, and he is currently a professor in the Department of Electrical and Computer Engineering at Princeton University, as well as the director of the Keller Center for Innovation in Engineering Education. Naveen and his group work in the adaptation of integrated circuits and systems to emerging applications with special focus on circuits and algorithms for low power consumption systems and components for low power processing and communications in advanced and emerging technologies. His talk today is titled AI Meets the Real World, Machine Perception Through Sensing Technologies That Preserve Structure. Naveen, thank you very much for accepting our invitation. We're looking forward to hearing about your research. So the stage is yours. Thank you.
Well, thank you very much. I'm going to go ahead and share my presentation. Please let me know, Virginia and others, if there's any issues with audio or any issues with visuals or anything like that, but I'll assume all is well, unless you tell me otherwise. Well, it's a great pleasure to be, unfortunately, not there with you, but we don't let silly little things like global pandemics stop us from doing what we do, which is sharing our ideas. And so I hope that I'll be able to speak a little bit about things, but that this will really be an opportunity for us to have a conversation. And I realize Zoom can make it challenging, but at times where you feel like there's something interesting that I'm saying and you'd like to hear more about it, please find whatever way you can to just get my attention, and I would be more than happy to talk about those sorts of things. I really hope we can have as rich an exchange as possible. So to try and facilitate that, let me go ahead and get started. Before even introducing the topic, I'll just mention that this work is in fact a really broad collaboration, of course, between myself, but also between very close collaborators, my colleagues, Professor Sigurd Wagner and Professor Sturm. And then, of course, the folks who do the real work is a whole group of students, and Sigurd, Jim, and myself, we run it a little bit like the names are shown here, which is that the three of us try to stay out of the way of all of the students who are listed across the middle. And so, please find ways to connect with all of my colleagues. They'll all have important things to say. Let me go ahead and start talking a little bit. So the title of the talk is AI Meets the Real World. And look, AI has excited us in so many ways, but of course, it's really only meaningful in some sense if we can interact with it and use it extensively. And at the end of the day, that requires technologies, the kinds of things you and I work on. And I want to talk a little bit about technologies, not just for computing, which of course connects closely to the algorithms in AI, but also technologies that actually make contact with the real world. Those are the sensors and the actuators. You may think of AI as this thing that is an abstract concept for mathematicians. I want to really change your view on that. I believe that for AI to move in the ways that it needs to really maximally have impact on the world, it's going to need physical technologies that can help do it right. So let's talk a little bit about that. Perhaps the starting point in all of this, and what many of you likely know, is that the truth is machines have reached an inflection point. They have started to achieve capability in tasks that we've traditionally associated with cognition at the level of humans. So these are tasks like vision, speech, strategic gameplay. And this is really remarkable. This has the potential to, I believe, completely change the relationship between technology and society, using machines in new ways. But if we go a little bit further along that path, what we find as we try to deploy this capability in the real world is that in many instances, in most instances, this capability fails gloriously. And these are just a few examples. And there's all sorts of reasons for this. The truth is the real world is a complicated place. It's governed by complicated physics, which leads to processes whose statistics are complex in that they're non-stationary. They can have all sorts of biases like human will. There can be logical perturbations, so on and so on. And so if you look at these images, you might say to yourself, well, this is really a problem for the algorithms people, the mathematicians. What am I, as a technology developer, supposed to do about this? And so let's talk about that. And let's talk about that by getting to the heart of what machine learning, which is driving a lot of these AI algorithms, what machine learning is actually doing. And the highest level point I want to make is there's nothing magical about machine learning. Machine learning is really simply about figuring out how to model the way that meaning is encoded in data, the way that semantics are encoded in data. And if you just think about this, it's a very sort of, logical process. If your data happens to be images, well, meaning is encoded in the way that that pixels cluster together. A certain clustering of pixels corresponds to human pedestrians. A certain clustering corresponds to bicyclists. And so it's really that clustering of that spatial arrangement of data that's meaningful here. So what do? Well, the data scientists say, let me build a model to represent that meaning. And we typically use something called a convolutional neural network, for example. What is that? Well, it's just something that takes a patch of pixels, applies a correlation filter to it to figure out what it's looking at, and then does that repeatedly to try and build a larger and larger patch, a larger and larger receptive field. So really, that's what this is about, recognizing that data is encoded in spatial arrangement of pixels, and then building a model that tries to essentially make decisions based on how pixel patches are encoded. Similar sort of thing for other models like language. Here, the information is encoded in the sequential structure of how letters lead to sounds, lead to words, lead to sentences. And so we just need a model that captures that sequential structure. And you do that by introducing some memory in your neural networks. You might use a long short-term memory unit and so on. And similar sorts of things for other physics that we might encounter in the real world. But what is all the point here? Well, the insight to take away here is that what we're really relying on in data science to build machine learning models is structure. If there's something that we know about our data, structure is really the way that data is organized and how that has meaning, not just the value of each of the instances of data. But if we have structure, this can help us build better models, or even build models at all. And so this is all about structure, and then how can we take advantage of that structure in the models we build. Well, those of you who work on sensing technologies are really critical to determining what structure there will be in data. And that's because sensors are going to be the source of some of the most important data in the future. And so I want to give you an example. One of the ways that we think about our work in sensing to very explicitly align with the problem of machine perception, these models that we want to build for machine learning, is by thinking about how we can introduce structure in data. How can we preserve, in particular, very rich structure of the real world in the ways that we do sensing? And one of the things that we've been exploring is what I call physically integrated sensing. The idea here is to associate sensors directly with objects, and in particular with embedded signals that are generated by objects. And the reason is associating sensors with objects has semantic meaning, because the ways that objects interact says something about the activities that are happening, for example, in an environment, and maybe even the underlying intentions. Okay, and it structures the data explicitly and with invariance in that way. So to give you an example, I can click forward here. Imagine that I attached a sensor to this dumbbell. Well, then that sensor is always going to tell me about the interactions happening with that dumbbell. And that's meaningful because when I use a dumbbell, it might mean that I'm doing exercise. Or when I use utensils, it might mean that I'm engaged in a complex task like cooking. Or if I attach sensors to a notebook, a cup of coffee, and a laptop, it might mean that I'm involved in doing work in an informal environment or something like that. And so this invariance introduces structure, and that structure has relevance, for example, to the complex tasks that we're doing. And so directly associating sensor data with embedded signals enables this invariant semantic structure. And it also, by the way, gives us access to diverse modalities. For example, I can sense vibrational modes in some of these utensils, which I couldn't have picked up, for example, through a vision sensor. So how does this help? Well, let's just contrast this so-called, embedded physically integrated sensing with maybe the more typical form of sensing, or the kind of sensing we often associate with machine perception today. And I'm going to broadly categorize that as remote sensing. Okay. An example of this is vision. And the key here is that while in physically integrated sensing, the sensors are directly coupled to these embedded signals to give me that invariance. In remote sensing, they're not. So imagine that I have a camera in the corner of a room, and it's picking up the image here. Well, the problem is, in a dynamic field of view, what exactly each sensor is picking up, each imager pixel is picking up, changes. And so now it becomes an algorithmic problem to resolve that invariance, to figure out what I'm looking at. And that's essentially what that convolutional neural network does. It essentially applies a correlation filter to a patch of pixels to figure out what it's even looking at. And then through the depth of this network, it builds up the semantics into bigger and bigger features, bigger and bigger things you might be looking at. The challenge is you now need essentially a correlation filter for every possible thing you might be looking at. And that's what we typically call the width of the network, or the number of output channels in a layer. And if you look at one of these networks in depth, that's essentially what it's doing. In the earlier layers, it's essentially trying to identify edges, and edges of all directions. And then in the later layers, it starts to compose those edges together. Some of them go towards forming an eyeball, or some of them go towards forming the back of a chair. And then as you go deeper and deeper, those eyeballs get composed into faces or into entire furniture like a chair. And then you can ultimately figure out that what I'm looking at here is a group lunch that was happening at Princeton somewhere. And so this works, these algorithms work, but you can see this ground up learning has a lot of complexity if we don't exploit structure from the start. So now there's an interesting question. What kind of sensors should I build? If you tell me that you need to introduce this structure in data, what sensors introduce structure, and what kind of structure do they introduce? And then what kind of models should I build to take advantage of that structure? Well, those are all open-ended questions. And so we need to be able to generate data sets to figure out what kind of sensors would be beneficial. And so what we actually do in our work is we synthesize data. We use a process called Monte Carlo synthesis, where we use these 2D, these 3D rendering tools, software, where we can now define underlying distributions, statistical distributions, for how objects might be placed for different activity classes like dining or cleaning or cooking or working. So now we can create these randomized scenes corresponding to different activities. And this becomes truly an inference process where we need to determine which distributions certain data samples are drawn from. The important thing is, because we synthesize this data, we can emulate any kind of sensor we want. We know everything about this scene by construction. So I can emulate any kind of sensor and then ask questions like, what kind of structure did it introduce? How should I take advantage of that structure through the right machine learning models, and so on. We do this for static scenes. We also do it for human activity videos. And so using a Unity 3D, this is a 3D gaming engine, we can define underlying statistical state transition diagrams and then start to generate videos for different activities too. So this is great. It helps us now explore some of those questions around what kind of sensors I should build. And then from these, I'm just going to give you an example of the kind of analysis that we do. Now that we've generated these scenes, we could say, well, what happens if I have a sensor that gives me the location of these individual objects? And from that, maybe I can generate features, for example, that correspond to the distance between certain objects and humans, because if a human is close to an object, that might mean it's being actively used towards some sort of a task. And then we can start to say, okay, what machine learning models will help me better identify what the human activities are? And then we can evaluate how well they work compared to sensors that don't preserve that structure. And so this is an analysis where we're using these PI sensors that give me that structure, and then through that deriving these very semantically meaningful features. And what we're evaluating here is how quickly can I train a model, a machine learning model, for learning these human activities. So this is called the sample efficiency of learning. And you can see here with this PI sensing, we can do this much more efficiently, with 40 times less data, for example, than we could with vision sensing using one of those complex convolutional neural networks. And so this is very interesting. We can analyze all sorts of other aspects as well, how well these models generalize, how well I can transfer them from one task to another task, all sorts of things like that. Now, an interesting question becomes, though, these embedded sensors sound great. They give me that structure. But Naveen, what are you going to do? Are you going to attach a sensor to every ice cube and hope that we can then, do this better perception? Well, that sounds like it's got a very high deployment cost. And so indeed, what we really want to do is fusion across sensors. Some sensors will have a high deployment cost, but they'll give me very rich structure. Some sensors will have a very low deployment cost, but they won't give me that structure. And so how should I start to combine different sensors to address sort of the whole range of issues that might be faced in building full systems and deploying systems? And so this then brings me to the topic of sensor fusion. Now, let me just say, in my view, sensor fusion is a grand challenge of machine perception. And the problem here is basically that you've got two different sensor streams. The question is, how are the semantics, how is the meaning encoded in each of these streams? And then how can I combine them? How can I create a common representation that exploits the meaning in both of them together? And so here's a very naive example of sensor fusion. In PI sensing, I mentioned to you that we have kind of the semantics intrinsically because, when I interact with objects, those objects indicate what activity I'm involved in. So that's intrinsic there. On the other hand, in vision, I have to learn that semantics, and I do that through the depth of this network. But then at the end, I've built up that semantics. And so the common ground here is really at the level of these final semantics, but now I have these very isolated representations. They're not really helping each other out very much. They're just, once they finally learn the overall meaning, coming together, right? And we can start to explore, if you take vision and then you start to add a little bit more and more and more of these PI sensors, things get better. You can learn with less training data, and it looks good. But it's a fairly naive approach. What would be much better is if we had a very comprehensive integration of these representations so that they can help each other all the way along. And so I won't go into all of the details here, but one of the areas that we're very focused on is models for sensor fusion that combine vision with PI sensing. And this is some data from one of the more generalized sensor fusion models that we build that combine vision, but then by doing this in a more comprehensive way with PI data can significantly reduce the training samples, the sample efficiency once again. Okay, so this was a little bit of a background on if you had sensors, how would systems today that really exploit artificial intelligence and this amazing capability that artificial intelligence gives us, how would artificial intelligence exploit these sensors? And so that was a little bit of background on that. You can see that the right kinds of sensors can make all the difference for AI systems. But now let's talk a little bit about what you and I do, which is build these technologies for sensing. What are the right technologies? How am I going to deploy them? You can see that in our research, the focus is on deploying large numbers of sensors that can be extensively integrated with objects in the physical world. And so to pursue this, we have been using a particular technology, a technology called large area electronics based on thin film processing. So many of you might be familiar with this. This is a technology that's processed using low temperatures. And because of that, you can process them in these enormous deposition systems. And so what that means is you can, in fact, fabricate systems today on sheets that are 10 square meters, 3 meters by 3 meters. And in fact, this is how the flat panel displays that I'm looking at and that all of you are looking at are fabricated on these enormous substrates. And then they get cut down into these various screens that we all use. And integrated into these screens are transistors and sensors or actuators, little pixels to generate the images that we have. A very interesting capability. And in fact, because it's low temperature, you can also use substrates like plastics that are flexible and form-fitting. Now, what's happening, though, is going beyond just display applications, there's a lot of interest in moving this technology towards general sensing. And one of the reasons is this low temperature processing makes me compatible with a really broad range of materials, which I can use to build transducers for sensing, for energy harvesting, and so on. And so I can generate systems like this one as an example. This is a sheet that's on flexible sheet that's on the order of a square meter, which integrates pressure sensors with 0.3 millimeter pitch. Very interesting form factor for these sensors. So this sounds really interesting. And this is something that we've been looking at Princeton for quite some time. We've built systems like microphone arrays that are integrated in wallpaper. We've built systems like large area imaging and classification. We've built strain sensing systems, so you can cover the sides of bridges and buildings with huge arrays of strain sensors to detect the structural health. Systems for monitoring human signals like electroencephalograms and electrocardiograms and so on. But how do these preserve structure? Well, let me give you an example. Let's take a look at this microphone array. So the interesting thing about a microphone array is they're microphones, so they can capture acoustic features, the sounds that are being generated. But because it's an array and because of the finite speed of sound, you can also figure out where that sound is coming from. You can do beamforming. So imagine that you've got a tap that's on, that's running, or you've got a window that's open and it's raining outside. Well, these generate audio features, and you can use those audio features to detect the activity that's happening. But also the location of that tap doesn't change, and the location of that window doesn't change. So that introduces structure, invariant structure. And if I start introducing a feature related to the direction of the sound, I can in fact infer with greater accuracy what activity is happening in an environment. So this is an example of a detection system that we built using the microphone array. So we built some of these systems. What have our experiences been? Let's talk a little bit about that. What we find is that this technology, large area electronics, you can build these flexible, these large systems, integrate sensors, sounds great. The challenge is when you do this low temperature processing, you end up with devices, in particular transistors, that are much lower performance than what you would get with regular silicon CMOS processing. I won't go into all of the device details here, but as one metric you might want to keep in mind, the FT, this is the unity current gain frequency. It's a metric for how fast the transistors are and for how energy efficient they are. And you can see that there's maybe 4 orders of magnitude difference in these two different technologies. So what do? Because a practical sensing system, of course, needs the sensors, which would like to be distributed and exploit this structure, but you also need control and processing. And so what you do is you build hybrid systems. You combine large area electronics with silicon CMOS. Now, when you do that, the challenge is the interfaces. You have on the one hand, a very scalable sensing technology. On the other hand, a very scalable computing technology and control technology. But in the middle, you have these very large number of interfaces as you attempt to scale up these systems. And so a lot of the focus of our work in building architectures for hybrid systems has been in using the thin film transistors. They're very low performance and very simple devices, but using them very selectively to reduce the number of interfaces so that you can let these overall systems scale up. And I just want to give you a notional idea for how we've approached this. And it's looked something like this. So imagine that you want to acquire a lot of information from a lot of sensors, but as the number of sensors increases, of course, you can incorporate more and more information. Now, in this notional example, I've ordered the sensors so that the most informative ones are towards the beginning. And so then at some point you get some diminishing returns. And so you have this sort of bending shape. But the challenge is, as you increase the number of sensors, your system complexity increases super linearly. And it does that because now you've got big arrays, you have longer wires, there's more noise susceptibility on those wires. All of these sorts of things impact system complexity. And so what you end up having is that as you increase the amount of information, your system complexity increases very severely. And what we would like instead of that is really a system or an architecture where the system complexity increases in proportion to the amount of information. And so then this takes us back to exactly how systems perform inference, how they make decisions based on sensor data. And in general, a decision system is based on taking maybe high dimensional data from many sensors, but then reducing that into low dimensional meaningful decisions through a process called feature extraction and then inference. And I won't go into all of the details here, but feature extraction essentially attempts to extract meaningful higher level structure of the data, and then inference attempts to make very specific decisions based on that. And so we've started to think about how we can use thin film transistor circuits to implement these stages to do this reduction of the interfaces. And the nice thing is, you can now start to exploit signal processing and algorithmic techniques that have been developed for feature extraction and inference. Start to really leverage your mathematician friends to understand how to build architectures. And let me give you an example. So this is a system where we do feature extraction using thin film transistors. It's a system that was used for building a tactile sensing skin. What a tactile sensor is a sensor that's in very close, maybe direct contact with the embedded signal. And so this was for structural health monitoring, where we were trying to detect early stage cracks. So what you'd like to do is create a very large array of strain sensors so that you can cover an entire bridge, but where you can detect cracks when they're very small at any location before they become big cracks. Now there's structure to this data. I have all of these sensors, not because they're all going to turn on. I have them because I want to know where cracks are generating and when those cracks are generating, even when they're very small. So really only a couple of these sensors gets excited when I'm interested in detecting a crack. And so how would you build a system like this? Well, one way to interface this and to acquire all the data is to build a sequential scanner. Access from each of the sensors one at a time. But of course, you can imagine that the number of acquisition cycles as your sensors goes from 1,000 to 10 million, the number of cycles goes up proportionally. The other thing you could do is build an active matrix, right? Create a two-dimensional array, read them out row by row, and then you read out all of the data in the column in parallel. And so that gives you a square root reduction in the number of interfaces and the number of acquisition cycles. But another thing to do is exploit the structure. If you know that only 1 or 2 or 3 of these sensors is going to get excited, that says that there's very few degrees of freedom actually that you're trying to sense here. And you can use a signal processing technique called compressed sensing, which simply says take random superpositions of this data. And if they're properly randomized and you know that there's only 3 degrees of freedom, only 3 things are changing, you can isolate which 3 things are changing. And so we do that. We build a very simple compression system because random superpositions are easy to do, even with my simple TFT circuits. And so I won't go into the details here, but basically from all of the sensors, we build a random switch array, which starts to take these superpositions by combining the data from all of the sensors and then reading them out. And we implemented the system. So this is a very small scale system as a proof of concept. It's an array of 20 sensors where we have 4 sensors here. Then we built these thin film transistors in our clean room facility at Princeton. And we have a custom CMOS chip to do the control and readout of these circuits. And so you can see here that, if you've got a case where you've got weights placed at 3 different locations, you can actually figure out where those are. And they can be at any 3 locations. So I've got data here where I have 3 sensors at a time, but at any different location. And the reconstructed resistance matches the actual resistance force that's generated on these sensors. Let me go a little bit further. Another example is using the classification stage to do this reduction of interfaces. And so for this, we actually took advantage of a technique in machine learning called classifier boosting, where the idea is if all you can do is build very simple classifiers, because that's all I can do with my simple transistors, TFTs, you can, in fact, combine them to build a very strong classifier by properly training those classifiers to support each other. And so I won't go into all of the details here, but there is some mathematics and we can derive some metrics based on information theory that show us that we can in fact build very robust systems using this. And so that's what we did. We built very simple thin film transistor circuits. It turns out that if you stack 2 of these transistors on top of each other, they kind of implement a multiplication. It's not ideal, it's nonlinear, but I can model that in the way that I build a model for my classifier, and then I can feed that to my machine learning algorithm. And in fact, I can do it in a statistical way because these transistors will have variations and so on also. But now I can train these classifiers in a way where I can, by using multiple classifiers, build a very strong classifier and then reduce the number of interfaces compared to the number of sensors that I might have had to otherwise interface. And so we built a large area imaging system where we have an array of photoconductors and then an array of these TFT-based classifiers. And you can see here that with just a few classifiers, you can in fact achieve performance that's at the level of some ideal, sort of high-performing machine learning classifiers, but you're interfacing very few number of signals now. Okay, so that was just a little bit of background on all of sort of the basic technique. One direction I want to talk about as I finish here is moving large area electronics to a regime where it can do wireless sensing. So as we really want to increase the number of sensors, many of these sensors will need to access through wireless links, wireless connections. Now, I mentioned to you that large area electronics is limited in its performance. And so it's a real challenge, but let's come back to that in a moment. If I could do this, the benefit large area electronics has is it can create these enormous sheets, these enormous arrays for doing this wireless communication. Why is that beneficial? Well, if I have many sensors distributed here, it turns out by generating electromagnetic radiation from across a big surface, I can now properly direct my radiation in very specific locations. So I can address these large number of distributed sensors by just controlling my antenna so that I can pick up exactly the sensors or the region of sensors that I'm interested in. Once again, remember the locations of these sensors and how these objects are interacting that the sensors are associated with gives me that structure. So now I can do this addressing of sensors in a way that's directly associated with that structure. And the reason this happens is that if you think about it, if I've got a sensor over here, I can sort of create a phased array that then directs the radiation pattern here. And if I can build a larger and larger aperture, as I'm showing as I go from this case to this case to this case, that aperture can be more and more specific, more and more narrow. I can direct my radiation more and more controllably to a specific location. And what's interesting is that if you make your aperture big enough, you can actually operate in what's called the near field. What that means is, from the point of view of a sensor that's over here, if the dimension of my aperture makes it not look like a point source radiator, so if the dimension of my aperture is on the same order as the wireless distance, then this doesn't look like a point source radiator, and I have this additional geometric degree of freedom, which allows me to create very rich radiation patterns. In fact, I can focus my beam directly at one location. And so this is something that's very compelling to do for large area electronics, but the challenge, as I mentioned, is that the achievable speeds have been very limited. And so one of the things we focused on recently is boosting the speed of large area electronics technology so that we can build high frequency wireless systems, but which can achieve unprecedented aperture sizes to enable some of this wireless capability. I won't go into all of the details here, but when you talk about boosting the performance of a transistor, there's two metrics you're concerned with, something called the unity current gain frequency, or the FT, and I mentioned this a little bit briefly before, and then also something called the unity power gain frequency, or the Fmax. And some of the approaches that we've taken to boost these involve to increase the FT using self-alignment. That reduces the capacitances and allows my transistors to operate more quickly. And also reducing the channel length. And that allows my transconductance of my transistors to be increased. Now, interestingly for Fmax, I can also reduce the capacitance and also improve the transconductance. You see that this term FT appears here, but I have an additional opportunity. I can reduce the gate resistance, and that can boost my Fmax. Now, this is very interesting. It turns out that with low temperature processing, the quality of your semiconductors is limited, but you can still build high quality conductors. And my gate is a conductor. And so in fact, what I can do is this self-aligned process to reduce the capacitances, but I can also use low resistance gates. In this case, we use a composite gate metal for our thin film transistors of chrome, aluminum, chrome to reduce the resistance. Once again, low temperature limits the quality of your semiconductors, but it can still allow you to build very high quality resistors. And so what you can do is achieve very large Fmaxes. We achieve Fmaxes of 3 gigahertz routinely in the lab. So interestingly, our Fmaxes, because of this dependence on the gate resistance, can, for these low temperature TFTs, be significantly higher than FT. And so what that tells you is build circuits that are Fmax limited, not FT limited. And you can start to exploit very high frequencies now. And so that's what we did. The first thing that we did is we built a RFID reader array. So you can build a sheet that covers a table. And you can imagine that these objects, like this cereal box or this bowl or this laptop, have little RFID tags on them, which maybe tell me what the battery charge level is, or what the temperature of this coffee is, or whatever the case is. And now, because I've got this large area technology to read out from all of these distributed objects, I can read out that data and create this spatial association. I won't go into all the details of this architecture, except to say that the fundamental block is a TFT oscillator. And using this oscillator, I can read out the data from the tag. But the important point about this oscillator is it turns out that it takes advantage of inductors to resonate out the TFT capacitances. And so what you end up with is a circuit whose performance is only limited by the loss sources in this LC tank. And so once again, this is an Fmax limited circuit, because all I got to do is deliver power to compensate for that power loss in the resistance of the tank. And by the way, using large area electronics, I can actually build very high quality inductors because they can be large and they can have thick traces. And so I'm really exploiting the large area attribute of the technology. So this is a circuit that's Fmax as opposed to FT limited, and it allows us to build these robust 13.5 megahertz RFID reader arrays. But we can go further. This is a 1 gigahertz phased array that we built. So here we've got these oscillators, once again, Fmax limited circuits, and we then introduce some additional functionality to be able to phase, synchronize, and tune them. And now what you can do is, by properly tuning the phase between them, you can direct the radiation in various different directions. This is a system setup where we measured the far field radiation pattern. And you can see, using this phased array, we can now direct the radiation, like I suggested a few slides ago, in specific locations to acquire data from specific sensors in a way that's now accessing them structured around the physical distribution of objects that these sensors are associated with. Once again, it's an Fmax limited circuit because it uses these oscillators. But we can go further. What we've done is we've created these large area antenna arrays. These are basically patches of little antennas, and we have connections between them. And these connections, if you turn them on or off, they change the surface current distribution in this array. And it turns out that how the surface current is distributed directly determines your far field radiation pattern. And so by changing these switches, you can now create various different radiation patterns, like I'm showing over here. An interesting thing about this architecture is, because I'm using my thin film transistors as switches, I use an inductor once again to resonate out the capacitances. But interestingly, the power loss in this transistor is very low, because I now have a very small voltage across the drain and the source. So if you're interested in building Fmax power loss limited circuits, in fact, the power loss in this circuit can be very low, and that's what allows us to go from that 1 gigahertz phased array to a 2.4 gigahertz antenna. And 2.4 gigahertz is significant because that is the frequency band that's used for most low power sensing. Now we can do all sorts of other interesting things. An interesting issue with this is it's a 208 transistor array. So a question you can ask yourself is, how do I figure out how to turn these switches on and off to generate these different radiation patterns? Actually, there's no analytical solution for that. So how we got these radiation patterns was really through a process of simulation to figure out what the right switch configurations is. But now what we've started to do, I'll skip some of this stuff. Now what we've started to do is build feedback systems. So systems that take this reconfigurable antenna array, but figure out how to control it using machine learning models. So you can actually use a feedback model for how to control the antenna array. Even though I don't know how to set those switches, there's no analytical solution, unfortunately, I can use machine learning to figure out how to set this high dimensional control plane for this antenna array. And so the last thing that I'll show you is that we essentially took advantage of machine learning models now, once again, to say that, hey, this antenna array, it's a two-dimensional structure of data. Remember those CNNs that I talked about for modeling two-dimensional meaning in data? Well, it turns out that we can use those to figure out how this two-dimensional arrangement of switch configurations now maps to a far-field radiation pattern. And using this, we can build these controllers that are given a desired radiation pattern and then can figure out how to set this control vector in order to generate the actual output radiation pattern. So really a co-design between machine learning and the sensing technologies, both for benefiting machine learning and for machine learning to benefit these sensing technologies. Okay, what I'm going to do now is I'm just going to post these conclusions. I won't go through all of them in great detail because I think I'd like to leave a few minutes for questions, but you can read the conclusions as you go, and I would be more than happy to answer questions if there are any.
Thank you very much, Naveen, for this very interesting talk. I'm going to now, there were no questions in the chat, so people who would like to make some questions, you can raise your hand and I will call on you. Naveen, maybe I'll start, so give people a little bit of time to think. So do you foresee, in terms of the technology, because these wall-sized large area electronics, there are systems for depositing the thin films on these large area substrates, but in terms of the microfabrication, do you foresee that it needs to be like a kind of a printing process to make these sensor and TFT arrays, or because the typical microfabrication processes are not geared for such large sizes? What is your thought on that?
Yeah, I mean, so it's a very good question, right? I mean, some of the systems that we've built here do push our transistors to get finer features, right? We have smaller overlaps and we have smaller channel lengths. And so we do use lithography processes to do that. And, so I think that there are pathways with some of the lithography processes, right? So some of these flat panel display fabrication techniques, there's questions. Can they scale to do the finer features that we're doing? And I do think that that's very feasible in the future for the kinds of processes, the kind of lithography processes that are used, for example, for displays. Now, of course, if we can do printing, that opens up a whole new scalability model and a whole new cost model. And I would say there's other factors too, not just printing, right? So lamination. So, these displays that we're looking at are these bonded constructs where you have a layer of sensors and then you have a layer of thin film transistors and you bond them together. And I think we'll want to adopt those kinds of techniques so that the different technology layers, sensors versus control circuits and so on, can be fabricated in the way that's best suited or optimal for them, but then we can take advantage of all of those different devices together. So I do think that, sort of printing techniques will be relevant for some of these layers. And, sort of other more lithography-based techniques might be relevant for other layers. And ultimately, that's a pathway forward. But certainly, while having that pathway forward, one should also explore, sort of the benefits that printing processes could give you for scalability and cost and so on. But I do think it's important for system design to be able to have some mechanism to build the full thing and then have ongoing mechanisms to refine each of the things.
Okay, thank you. Vanya?
Yeah, thanks, Naveen, for this really great talk and really exciting. So my question is, what do you feel is the biggest gain in using AI in the development and the usage of your sensors?
Yeah, great question. So there's two questions, right? There's two ways to think about this. One is we're building sensors to do better AI. And then there's the question, can I use AI to build better sensors? And that was kind of that last example where, we said we're going to use AI. We built the sensor and it has all of these transistors, and that's kind of like what we were able to do. But now, given what we were able to do, can I get AI to actually help me do the very challenging control problem? And so I do think that there's going to be a two-way street between, technologies helping AI and AI helping technologies. And we're already starting to see that. So in advanced chip design. AI is being used to do some of the complex placement and routing of, sort of high advanced node CMOS processes. People are using AI in slightly the same way that we're doing to build MIMO systems, multi-antenna, multi-input, multi-output systems, and figure out how to construct them together, where like the analytical design approaches are not very tractable or not very manageable. So I do think it's going to be a two-way street. What are all the ways? I can only imagine. Your guess is as good as mine. And so what I'll tell you is that as technology developers, we should get involved in AI on both of those streets. And so I do think there's a lot of potential here. And so let me just perhaps drum up some excitement for us to fearlessly get involved in AI.
Jonas?
Thank you. I apologize for not having a camera at this moment, but let me say thank you for this very exciting presentation. I'm sure you're aware of works on memristors for implementing neural networks. Can you say what is the major thing that's missing to implement them in such a system that you are developing?
So do you mean memristors in silicon CMOS chips for computation or in the sensing arrays? I could speak to both of them, but let me know which one you're more interested in.
I mean more in the interface part. So doing some of the compression, for example, by in-memory computing using non-volatile memristors.
Right. So in-memory computing is actually a very general concept. It's really meant to solve the problem of the memory bottleneck, right? Where you have data that's stored in an array, and now you need to move it out of the array to do computation, and that moving is very costly. But indeed, the way that Jonas is describing this, you could also have sensor data in an array, and now you want to move sensor data out of the array, and that movement is costly in the ways that I described, right, related to the interfacing. And so certainly having memory devices that can store, for example, important parameters of a machine learning model or of some kind of a estimation model is useful. I think that the need has been perhaps a little bit less in the large area sensing space that I talked about, because you're not really using the sensing technology for energy efficiency and so on. On the other hand, I think in-memory computing has been critically important in high performance AI chips. And I will say that sort of resistive memory is a very interesting direction for in-memory computing, and one that my group has been looking at quite a bit, but it's also very, very challenging. And it's challenging not at the level of just implementing the basic compute function, but the truth in these computing platforms is you need to do many things. You need to be able to change the data. You need to be able to properly map the data, interface to the software stack. These are all things that I think are really important and I'm interested in our research, but didn't get the chance to talk about in the talk. And so some of the biggest challenges in integrating those technologies is really just integrating them architecturally in ways that are feasible. I hope that was useful, but I'm certainly happy to chat more about that if you're interested.
It was very useful, and I share lots of your opinion on this. So thank you for that.
João?
Hi, Naveen. Really nice. I see that you've gone really beyond the megahertz oscillators now. It's going to be very difficult to catch up to the gigahertz with, for example, with MEMS. One question is probably very naive, but when you were talking about this AI and structured sensors, I was thinking, are people considering somehow hybrid models? For example, we are cyclists and pedestrians, probably 95% of them have cell phones on, which could help the car sensors understand that they are there, but it's not enough, right? Because maybe 5% of people don't have their cell phones on, or they're out of charge, and then your camera will have to do some kind of detection. So yes. I was wondering, if you are considering this kind of mixed sensor implemented, and then something more general like vision or something.
No, excellent question. And indeed, that is really where you want to go, right? It's fusion between all the different kinds of data streams. Some of those might come from a vision sensor that's inside a car, but some of that might also come from what we call vehicle-to-vehicle communication or vehicle-to-pedestrian communication. So these are devices that another vehicle has or a pedestrian has, and they can send information back to the system. I do think that that's a very active area of research and an area that we're interested in as well. We've focused on it less for autonomous driving, but we focus on it, for example, for smart industries kinds of applications where humans are interacting with robots and industrial, automated equipment. But you're absolutely right that, leveraging, sort of more of this embedded sensors together with the vision sensors is the way to go. One of the challenges in autonomous driving is that you need to be able to make the decision in real time because the car is moving. So it has to be low latency. And some of the challenges have just been the reliability of the network link, of the communication link between an off-board sensor, like, on another vehicle or on a stop sign or in a traffic light that's telling my autopilot system what to do. That there's been some reliability concerns around that, really because of the communication link and the synchronization between those sensors. And so I would say that the first set of systems are using vehicle-to-vehicle communication or vehicle-to-infrastructure communication, but not necessarily for autopilot features, for more high-level planning. But as some of those issues get resolved, you can certainly see things going in that direction, even for autopilot.
Thanks.
Vanya?
Yeah, just a general question. You showed the table with the surface covered with a large area arrays of sensors. Do you have an idea of the power that system will consume to be on for 24/7?
Yeah, so it's interesting. One of the things you take advantage of in a system like this one, for example, is that the movement of these objects is slow, right? If I put a coffee mug down, I'm very aggressive. So I sip my coffee every 30 seconds, but I still have 30 seconds in between, the time that these objects move. And so one thing you can do to meet the power constraints is you actually, in this system, we actually turn these oscillators on kind of in a active matrix manner. And so only one row worth of them is on at a time. In this particular system, the actual power envelope was something like 20 milliwatts. That's the power basically for just one set of oscillators, a subset of the oscillators that are on. And that can be very reasonable. It can be reasonable for two reasons. One is because these are actually deployed on the infrastructure, you might be able to directly power them from a power source. The other thing is, and we've explored this in some of the other systems, because you have large area, you can also integrate energy harvesters. For example, photovoltaics that have a large cross-section and can harvest a lot of power. And for example, our strain sensing system did exactly that. So we had built-in power management circuits in some of the CMOS chips that were coupled in these hybrid systems. So the power is a very important question, and you look for creative ways in the application to be able to address it, and you need to. But there's often a lot of opportunities to do that at the system level, which is why I think it's really important to take our sensors up to the system level. There's a lot of opportunity to solve challenges at that higher level.
Okay, are there any other questions for Naveen? João Pereira?
Hello.
Hello.
Hello?
Yes, go ahead.
Okay. I have a question. If it's possible, if the array of the transistors, for example, is in a synthetic scheme, so it can use to say the word envolvido. That is involved in the for example is in the heart, in the liver, for detection, is for censoring.
I think you're asking, can we start to think about using these technologies for really sort of close interfacing with biological tissue and organs?
Yes.
To do biological sensing?
Yes.
And certainly you can. There's interesting work where people have used even biologically resorbable substrates. So you build sensors, and use the substrate almost to transfer them, and then they get moved over to those organs. Now, that's very far out there. But actually, my colleague at Princeton, Professor Sigurd Wagner, has really been exploring, sort of substrates that are very stretchable, very compliant in ways that's necessary if you want to interface them with tissue, because tissue tends to be soft and moving all the time. And so in order to be able to do that in a way that doesn't cause a histological response from the tissue, inflammatory response from the tissue, you need to have substrates that have the right sorts of flexibility. In fact, a postdoc from Princeton is at EPFL. Her name is Stephanie Lacour. So some research in that area of the kind that she's doing might be of interest to you, but there's many people who are doing that sort of thing. So a very interesting area, very interesting form factor for also integrating electronics with tissue and organs.
Okay, thank you.
So one last question, anyone? Okay, if not, I think we can conclude the formal part of the seminar. Naveen, I'd like to ask if you could stay on just a little bit afterwards. I first like to again thank you for accepting this invitation, and I'm sorry that we're not able to take you out for dinner now by the sea. So hopefully, hopefully next time we'll be able to do that. And thank you once again. If anybody has questions, Naveen will stay a few minutes after we end the formal part of the seminar. If you want to talk with him just informally. Okay.